This is our fifth of 6 videos on 9.3.4, this time looking at amphiprotic and polyprotic substances. In the previous video we touched upon amphiprotic when we were looking at neutralization. So what is an amphiprotic substance? An amphiprotic substance is a substance that can act as a proton donor and as a proton acceptor, hence act as an acid or a base in different situations, and that's called amphiprotic. And some common examples are water. Water can actually accept and donate protons. The bicarbonate ion can accept and donate protons, same as the hydrogen sulfate ion, dihydrogen phosphate, and hydrogen phosphate. We've seen them in our buffer example. So they don't always donate and accept. They don't donate and accept in every single situation, but they donate and accept in certain situations. If you place any of these species with a strong acid, the strong acid wants to donate protons, so when you put these with a strong acid, they'll act as a base. They'll accept protons from the strong acid. But if you place them with a strong base, what they'll do is they will act as an acid. They'll donate protons to the strong base. So if you put them in water, for example, some of them will act as bases, some will act as acids when you put them in water. But the main idea is if you put them with a strong acid, they'll act as bases. If you put them with a strong base, they'll act as acids. So the amphiprotic bicarbonate ion and the amphiprotic hydrogen phosphate ion, there's some examples here, putting them with strong acids and with strong bases. Strong acids represented by H3O+, strong base represented by OH-. Have a go at these equations and check your answers in just a second, so pause the video. Okay, time to check your answers. I'll let you check them and decide how you went. One thing to note is that even though these are all weak acids and weak bases, amphiprotic things are always weak acids and weak bases, I've put the non-equilibrium arrow here, and that's because I've put them with strong acids and strong bases, and strong acids and strong bases make things go to completion. So when you put the bicarbonate ion with a very strong acid, the reaction will go to completion. That strong acid will turn all the bicarbonate into hydrogen carbonate because that strong acid is donating protons. When you put the bicarbonate ion with a very strong base such as hydroxide, that hydroxide will accept protons from the bicarbonate turning into carbonate. So it's because you're mixing with strong acid and strong base, the arrow is straight ahead. There's no equilibrium there because the strong acid and strong base won't allow the reverse reaction to take place. So what's a polyprotic substance? Well, a polyprotic substance, well, before we look at that, what's a monoprotic substance? So a monoprotic acid can donate only one proton per molecule, and some common examples are hydrochloric acid, nitric acid, and acetic acid. And don't forget that's the one hydrogen there on the carboxylic acid group that can donate the proton. So they're monoprotic acids, mono meaning one. But a polyprotic acid can donate more than one proton per molecule. Polyprotic acids can be diprotic, meaning donating 2 protons per molecule, and a common example is sulfuric acid or carbonic acid. In theory, they can both donate 2 protons per molecule, or they could also be triprotic, which means donating 3 protons per molecule. And some examples there are phosphoric acid and citric acid. We know that complicated structure of citric acid, 2-hydroxypropane, 1,2,3 tricarboxylic acid. The fact that it's tricarboxylic or 3 carboxylic acid groups means it can donate 3 protons. We know it's weak. We know when we put it with water, it rarely donates 1, let alone 2, and rarely ever 3. But when you put it with a strong base, that strong base might force it to donate all 3 protons, and that's what we're going to look at right now. Polyprotic neutralization reactions. If you've got a diprotic acid or a triprotic acid, and you add it to a strong base, that strong base, being a strong base, really wants protons. It'll force this carbonic acid to give away all its protons, even though it doesn't really usually want to in water. Sodium hydroxide is not water. This is what's important about the Bronsted-Lowry theory, the fact that the solvent is very important in determining the properties of an acid. If you put carbonic acid in water, it is not a strong acid. It will rarely donate 1 and almost never donate 2 protons. But as soon as you change the solvent, and that is solvent sodium hydroxide being a strong base, it'll basically rip both protons off the carbonic acid. So the reaction will go to completion. So when you put this otherwise weak base with sodium hydroxide, the sodium hydroxide will force it to go to completion. Every carbonic acid will donate all its protons, and you'll get this reaction here. You get carbonic acid plus sodium hydroxide goes to sodium carbonate plus water. But if you put this carbonic acid in water, it dissociates in a stepwise fashion, we say. So being weak, it's an equilibrium, so some carbonic acid will donate a proton to the water, producing bicarbonate ion and hydronium ions, and some, a very small amount, will donate their protons to water to produce the carbonate ion. It says here underlying conjugate base. Let's underline the conjugate base. Here is our acid. So here is our conjugate base. But we call this a conjugate base. And look here now, this conjugate base itself now is acting as an acid donating protons and forming this second conjugate base. And so because the bicarbonate ion is the conjugate base of carbonic acid, even though it can act as an acid, it's very unlikely to. It's a weaker acid, than the carbonic acid, and less likely to dissociate. So every time you have a polyprotic acid, when you react with water, yes, they can donate 1 sometimes, yes, they can donate 2 sometimes. In the case of phosphoric, yes, it can donate 3 sometimes. Each dissociation is less likely than the last because every one of these new acids we're producing is actually the conjugate base of the previous acid. But because these things can undergo a stepwise dissociation, they form a series of salts with different pHs, and the pH of these salts increases with each dissociation, i.e. the anions are the conjugate bases of conjugate bases, etc., etc. So hydrogen carbonate is a weak acid. Sodium hydrogen carbonate is an amphiprotic salt, but it's weakly basic in water. It will accept protons from water. And then sodium carbonate is just a weakly basic salt, but it's a little bit more basic than sodium hydrogen carbonate. And there's a sort of question that's come up a few times to trick students about polyprotic neutralization reactions. And the question is something like this: hydrochloric acid is a strong acid, and we know that citric acid and carbonic acid are weak. So we've got strong, weak, and weak. Now we've got 200 mils of 1 mole per liter solutions of all 3 acids. So we've got the same volume and the same concentration, hence the same number of moles of citric acid, hydrochloric acid, and carbonic acid. And the question is, which will neutralize the most sodium hydroxide? So let's think about it. So we know we've got 200 mils of 0.1 mole per liter solutions. So number of moles is concentration times volume, which is concentration is 1 times 0.2. So we've got 0.2 moles of hydrochloric acid, 0.2 moles of citric acid, and 0.2 moles of carbonic acid. And we've been told HCl is strong and these two are weak. Which will neutralize the most sodium hydroxide? And this is a trick question because students see this word strong and weak, and they think, oh, hydrochloric acid is strong, it must neutralize the most sodium hydroxide. But that's forgetting what happens with polyprotic acids and strong bases. So let's have a look. If we react the hydrochloric acid with sodium hydroxide, 1 hydrochloric acid molecule will neutralize 1 sodium hydroxide molecule. So if we've got 0.2 moles of hydrochloric acid, we can neutralize 0.2 moles of sodium hydroxide. But if we react that sodium hydroxide with the carbonic acid is, let's say, carbonic acid is diprotic. And I think I haven't balanced that equation correctly, we'll talk about it in a second. So carbonic acid is diprotic, therefore it can actually donate 2 protons. Therefore carbonic acid, even though it's weak, when you put it with this strong base sodium hydroxide, 1 carbonic acid can actually neutralize 2 sodium hydroxide molecules. Let's get rid of that, that's obviously not correct there. And look at this third case, citric acid. Now we know citric acid is triprotic. Now its usual molecular formula is C6H8O7. I'll just put the H3 at the front to recognize they're the 3 protons it can donate. When it reacts with sodium hydroxide will actually try and take away all 3 protons because it's a strong base. And therefore that 1 citric acid molecule can actually neutralize 3 sodium hydroxide molecules to produce sodium citrate and water. So don't be fooled by the strong and weak when things are reacting with strong bases, because the strong bases will force all acids, no matter how weak they are, to give up all their protons. Because don't forget, when we say something's strong and something's weak, that's when we say this acid is strong in water, and these acids are weak in water. Strong and weak still relate to the water solvent. But when you're mixing them with a strong base, we have a new solvent now, and all acids are strong. All acids are completely strong, they completely ionize when you put them in the solvent, such as sodium hydroxide, which is a strong base. So have a look at some of those questions in the HSC, they're very important to do.